Welcome everybody. Just thought I'd make a little video to try to help you guys a little bit with the homework. So these are just basically some sample calculations that illustrate some ideas in modular arithmetic. So start out real simple. Suppose you want to find the, well, you want to basically simplify this number in z mod 6. So looking at the 12,345, the equivalence class represented by 12,345. So these square brackets around here, remember, mean that we're working with a whole set of integers. Basically this number plus multiples of 6 times the integers. And as I mentioned, one way you could figure out the least positive representative for this would be to simply use division. So if I get out my handy dandy long division here, 6 divided into 12,345, you work it out, you get remainder 3, which shows you that in fact 12,345 is 6 times 2057 plus 3, right? But when I'm working modulo 6, when I simplify that, the multiple of 6 just becomes 0, so we can basically absorb that into the equivalent. We can just set that to 0 is what it boils down to, and so we're just left with 3. So this is kind of one way you can calculate. I don't always calculate that way, but if you can divide, sometimes you can actually do the division, other times you really can't, as we'll see. Here's another one, another way to look at this kind of problem. Here, it's windy out here. In a momento. There we go. So here, calculating the equivalence class, and you know, if there's ambiguity, sometimes I add a little like 1 here to tell you that I'm working with equivalence classes mod 11 in this one, right? In the first one, and then in my second example, I'm working with equivalence classes. Oh man, what have I done? Look at that. Goodness gracious. 6 I meant. These were 6, right? 6. Alright, there we go. And then in this one, in my second example, we're working with equivalence classes mod 11. Let's see here. So in the world of arithmetic modulo 11, we're allowed to treat multiples of 11 as if they're 0. That's the guiding arithmetic principle. And so if I want to emphasize that I'm working mod 11, I can put the little sub 11 down there. We don't always do that, but sometimes it's helpful. And anyway, so another important thing, maybe you haven't thought about this much lately, but if we're talking about a number, our cursor default is to use base 10, right? And when I say 12,345, what that means is you've got 1 copy of 10 to the 4th, 2 copies of 10 to the 3rd, 3 copies of 10 squared, 4 copies of 10 to the 1st, and 5 copies of, well, 1, or 10 to the 0. And so really, base 10 is a sum of powers of 10, right? And so if you're working modulo 11, that's nice because you know, we could work out that 10 is actually equal to minus 1 mod 11. And as such, 10 to the power m actually works out to, well, the equivalence class of 10 to the power m, right? And that's minus 1, and then we can bring the m back inside. And as such, minus 1 to the m is, well, that simplifies in the usual rules, right? If m is even, it's 1. If m is odd, minus 1 to the m is minus 1. And so down here, I have this, but then by the rules of modular arithmetic, which I will likely justify next class, the equivalence class of the sum is the sum of the equivalence. Oh man, I haven't, well, kind of. Alright, fine. So like if I wanted to write more, I could break this up into the sum of equivalence classes, and then the product, and then each one of those you can write the product of the equivalence class of 1, and equivalence class of 10 to the 4th. Anyway, it's fine that I didn't write all this down because, um, um, well, I'm just trying to show you how to calculate. So if I show you a less cumbersome way of calculating, I guess it's okay. But so 10 is congruent to minus 1 mod 11. And so that's the overriding idea, is we can use congruence to simplify the representative of an equivalence class. And so again, that congruence idea is that a multiple of 11 is 0 in this world. So I trade my 10 to the 4th for a minus 1 to the 4th, a 10 to the 3rd for a minus 1 to the 3rd, 10 squared for minus 1 squared, 10 for minus 1. And so we just get this alternating sum of the digits. 1 minus 2 plus 3 minus 4 plus 5, and so it works out to 3. As we, of course, we already found up here by division. I do think that this method of calculation down here, it can actually be very nice, especially if the number is bigger. Or some, divisibility for certain numbers is much easier than others, right? If we were looking at divisibility mod 9, right, then 10 is equal to 1 mod 9, so the it allows an even nicer calculation. I'll probably do that one in class. I'm saving that for class, because that derives the rule of nines that you might have learned once upon a time, maybe in elementary school or something, that a number is divisible by 9, or a multiple of 9, if and only if the sum of the digits in the base 10 representation of the number is actually equal to a multiple of 9. Now, here is a different example. Simplify 3 to this. Man, there's always some ambulance coming by here when I make a video. Anyway, 3 to the 70th mod 10. We want to simplify this. All right, mod 10. Mod 10 is nice because we're pretty familiar with arithmetic involving 10. So first of all, notice that 3 squared is 9, which is minus 1 mod 10. So that means that the equivalence class represented by 3 squared could just as well be represented by minus 1 mod 10. All right, and so if I do this calculation here, 3 to the 70th, I can trade for 3 squared to the 35th power, and then by the rules of modular arithmetic, which I probably should justify this exponent thing I keep using in class. We'll look at that. That gives me 3 squared to the, raising the equivalence class to the 35th power. Again, we're working mod 10, but that's minus 1. Then I move the power back inside, all right? And then I know minus 1 to the 35th is minus 1 because it's an odd power, and so I get 9. So what does this all mean? This means that the it means various things. One of the things it means is that 3 to the 70th is not a multiple of 10 because it didn't reduce to 0, right? So it's not divisible by 10. And not terribly surprising, I think. But perhaps more interestingly, this actually shows you that the last digit in the decimal expansion of 3 to the 70th would be 9. Let me explain why. And this is, of course, a very helpful comment for you guys for like problem 70. So here's the way to think about problem 70 in your homework. If we have AK minus 1, all the way down to A2, A1, A0, suppose these are the digits in a base 10 representative of n, a natural number. Then that means that if n is equal to this, it's actually, what that means is a sub k times 10 to the power k, a sub k minus 1 to the 10 to the power k minus 1, plus a2 times 10 squared plus a1 times 10 plus a sub 0. And of course, any multiple of 10 is congruent to 0 mod 10. So when we calculate the congruence, we calculate, the least positive residue, that is the representative which is smallest possible and positive. We have a theorem that says that that's also the remainder upon division by 10. But it's also, by this calculation right here, the last digit in the number. So to calculate the last digit, we simply have to simplify the number modulo 10. So that's how I knew that 3 to the 70th has the last digit of 9 here. Last digit of 3 to the 70th power is 9. I haven't written out 3 to the 3 to the 70th for you, but if I was to, um, and you could find it if you plug this into Wolfram Alpha. You can look at it in all of its glory. Wolfram Alpha will give you all 34 digits of it if you want to look. But it's 2.5 times 10 to the 33rd. And so if you think about that, that means it's got 34 digits, right? Like 1,000 has 4 digits. It's 10 to the third, So the last digit of these 34 digits happens to be 9. There you go. So what if, here's a hypothetical. What if you wanted to find the last 2 digits? Could we do that? I wonder if looking at something modulo 100 might do that. I don't know, I'd have to think about that some more, but just a thought. Now, let me just talk a little bit more about your homework, because you'd probably like me to do that. There is a most unfortunate typo, the most unfortunate typo in the LaTeX. We actually did an example, let's see here, like this one. If you really look at the thing I did at the end of last class, I've already done this problem more or less. Let's see here. Problem 66, I would say, is not that easy, but you can. I think that's the hardest problem in the homework. Maybe. I think I forget how many answers I found. I found multiple answers. There's not just one answer there. I mean, in principle, A and B are digits, so they have to be numbers from 0 to 9. I tell you that, So in the wild, there's, A and B are variables, so you got, you got, I guess you got 100 things to check. But I was able to use modular arithmetic to simplify it down to a question which I could just check 10 things and solve it that way. But there may be an easier way to do it. I don't know. It's been a while since I wrote these homeworks, and I'm not sure where I got that problem. I don't think I just made it up. I think I got it from some book or something. Maybe my brother. This right here, notice that there's a dot. See that dot right there? There's a dot right there. That was supposed to be 3.5. However, I've written it. I have inadvertently changed my middle dot to an upper dot, which is definitely not what I wanted. The point here is you're trying to show 15 divides this number. The key idea here is 3 times 5 is 15. All right, I'll explain more in just a second. For problem 67, here's a hint there. You're trying to show this is divisible by 7. If you can show that this number is congruent to 0 mod 7, then you've shown it's divisible by 7. That's the big idea here, is we can use modular arithmetic to answer questions about divisibility. For problem 70, I'll come back to problem 69 in a second here. For problem 70, we just need to reduce these numbers, modulo 10. The least positive residue, modulo 10, for these numbers would be the last digit. All right. Now you should explain why that is in your homework. I'm just giving you a hint. You need to understand that for yourself. Don't just use that as something I said and it's just true. You need to understand that for yourself. Why is it that mod 10, a number reduced, the least positive residue modulo 10 is the ones digit. And you should I showed you the proof of it, but you need to understand that for yourself as well. And so, make sure you include in your homework solution a discussion of that assertion. All right, you don't have to do it in every part of problem 70, but you should do it at least once, and then refer to that, something like that. Now, for problem 69, to further expand on my hint, here's a little lemma. If we have P and Q are distinct primes, and suppose P divides X and Q divides X for some integer X, well then PQ divides X. All right. So that's a lemma. It's not true if P and Q are not prime. For example, if we took P equals to 60 and Q equal to 6, well, 60 and 6 both divide 60, but certainly 60 times 6, which is 360, does not divide 360 does not divide 60. So this is only true, certainly, if p and q are primes. And here's the proof. It's kind of a corollary to Euclid's lemma. If we have x as an integer and p divides x and q divides x for some distinct primes, oopsie, distinct primes p and q, then there exists j and k for which x is pj and x is qk. Thus pj is equal to qk. And by Euclid's lemma, noting that p divides qk, we find that p divides q, or p divides k. But since p is prime, it must be that p does not divide q, otherwise q would have a divisor other than 1 in itself. Thus, p divides k. And if p divides k, k is equal to mp, and if we plug that back in, we get x is qk is qmp is p times mq, where mq is an integer. Therefore, pq divides x, which is the lemma. So that means for problem 69, to prove divisibility by 15, it suffices to prove divisibility by 3 and divisibility by 5. If we can show that that quantity, right, I'll bring it back in a second. If we can show that that quantity, you know, right here, if we can show this thing right here is divisible by 3 and by 5, then if we include the lemma in our homework solution, and we should do that, all right, we should do that, then we will have proved that 15 divides this as well. And of course, checking divisibility mod 3 and checking divisibility with respect to 3 and 5 is easily accomplished if you calculate how to simplify this quantity mod 3 and then also mod 5. One of those is pretty easy. The other one requires a little bit of calculation. Anyway, that's all I wanted to say for today. I hope this helps you guys. Have a good weekend. Bye.